CAN bus is a vehicle bus standard designed to allow microcontrollers and devices to communicate with each other within a vehicle without a host computer. CAN bus is a message-based protocol, designed specifically for automotive applications but now also used in other areas such as aerospace, maritime, industrial automation and medical equipment. Development of the CAN bus started originally in 1983 at Robert Bosch GmbH. The protocol was officially released in 1986 at the Society of Automotive Engineers Congress in Detroit, Michigan. The first CAN controller chips, produced by Intel and Philips, came on the markets in 1987. Bosch published the CAN 2.0 specification in 1991. In 2012 Bosch has specified the improved CAN data link layer protocol, called CAN-FD, which will extend the ISO 11898-1. CAN bus is one of 5 protocols used in the onboard diagnostics II vehicle diagnostics standard. The OBD-II standard has been mandatory for all cars and light trucks sold in the United States since 1996, and the EOBD standard has been mandatory for all petrol vehicles sold in the European Union since 2001 and all diesel vehicles since 2004. Applications: Automotive. The modern automobile may have as many as 70 electronic control units for various subsystems. Typically the biggest processor is the engine control unit. Others are used for transmission, airbags, anti-lock braking, ABS, cruise control, electric power steering, audio systems, power windows, doors, mirror adjustment, battery and recharging systems for hybrid electric cars, etc. Some of these form independent subsystems, but communications among others are essential. A subsystem may need to control actuators or receive feedback from sensors. The CAN standard was devised to fill this need. Industrial. Today the CAN bus is also used as a field bus in general automation environments, primarily due to the low cost of some CAN controllers and processors. Architecture. CAN is a multi-master serial bus standard for connecting ECUs. Each node requires a central processing unit or host processor. The host processor decides what received messages mean and which messages it wants to transmit itself. Sensors, actuators and control devices can be connected to the host processor. CAN controller. Hardware with a synchronous clock. Receiving. The CAN controller stores received bits serially from the bus until an entire message is available, which can then be fetched by the host processor. Sending. The host processor stores its transmit messages to a CAN controller, which transmits the bit serially onto the bus. Transceiver. Receiving. It adapts signal levels from the bus to levels that the CAN controller expects and has protective circuitry that protects the CAN controller. Transmitting. It converts the transmit bit signal received from the CAN controller into a signal that is sent onto the bus. Each node is able to send and receive messages, but not simultaneously. A message consists primarily of an ID, which represents the priority of the message, and up to 8 data bytes. The improved CAN-FD extends the length of the data section to up to 64 bytes per frame. It is transmitted serially onto the bus. The signal pattern is encoded in non-return to zero format and may be received by all nodes. The devices that are connected by a CAN network are typically sensors, actuators, and other control devices. These devices are not connected directly to the bus, but through a host processor and a CAN controller. Data transmission. CAN features an automatic arbitration-free transmission. A CAN message that is transmitted with highest priority will succeed, and the node transmitting the lower priority message will sense this and back off and wait. This is achieved by CAN transmitting data through a binary model of dominant bits and recessive bits where dominant is a logical 0 and recessive is a logical 1. This means open collector, or wired or physical implementation of the bus. The idle state is represented by recessive level. If one node transmits a dominant bit and another node transmits a recessive bit, then the dominant bit wins. So, if a recessive bit is being transmitted while a dominant bit is sent, the dominant bit is displayed, evidence of a collision. A dominant bit is asserted by creating a voltage across the wires while a recessive bit is simply not asserted on the bus. If any node sets a voltage difference, all nodes will see it. Thus there is no delay to the higher priority messages, and the node transmitting the lower priority message automatically attempts to retransmit 6-bit clocks after the end of the dominant message. When used with the differential bus, a carrier sense multiple access bitewise arbitration scheme is often implemented. If two or more devices start transmitting at the same time, there is a priority-based arbitration scheme to decide which one will be granted permission to continue transmitting. The CAN solution to this is prioritized arbitration, making CAN very suitable for real-time prioritized communication systems. During arbitration, each transmitting node monitors the bus state and compares the received bit with the transmitted bit. If a dominant bit is received when a recessive bit is transmitted, then the node stops transmitting. Arbitration is performed during the transmission of the identifier field. Each node starting to transmit at the same time sends an ID with dominant as binary 0, starting from the high bit. As soon as their ID is a larger number, they will be sending 1 and C0, so they back off. At the end of ID transmission, all nodes but one have backed off, and the highest priority message gets through unimpeded. For example, consider an 11-bit ID CAN network, with two nodes with IDs of 15 and 16. If these two nodes transmit at the same time, each will transmit the first 6 zeros of their ID with no arbitration decision being made. When the 7th bit is transmitted, the node with the ID of 16 transmits a 1 for its ID, and the node with the ID of 15 transmits a 0 for its ID. When this happens, the node with the ID of 16 will realize that it lost its arbitration, and allow the node with ID of 15 to continue its transmission. This ensures that the node with the lower bit value will always win the arbitration. The ID with the smaller number will win the right to use. Bit rates up to 1 Mbps are possible at network lengths below 40 am. Decreasing the bit rate allows longer network distances. The improved CAN-FD extends the speed of the data section by a factor of up to 8 of the arbitration bit rate. ID allocation: message IDs must be unique on a single CAN bus, otherwise two nodes would continue transmission beyond the end of the arbitration field, causing an error. In the early 1990s, the choice of IDs for messages was done simply on the basis of identifying the type of data and the sending node. However, as the ID is also used as the message priority, this led to poor real-time performance. In those scenarios, a low CAN bus utilization of circa 30% was commonly required to ensure that all messages would meet their deadlines. However, if IDs are instead determined based on the deadline of the message, the lower the numerical ID and hence the higher the message priority, then bus utilizations of 70 to 80% can typically be achieved before any message deadlines are missed. Bit timing: each node in a CAN network has its own clock, and no clock is sent during data transmission. Synchronization is done by dividing each bit of the frame into a number of segments: synchronization, propagation, phase 1 and phase 2. The length of each phase segment can be adjusted based on network and node conditions. The sample point falls between phase buffer segment 1 and phase buffer segment 2, which helps facilitate continuous synchronization. Continuous synchronization in turn enables the receiver to be able to properly read the messages. Layers: the CAN protocol, like many networking protocols, can be decomposed into the following abstraction layers: application layer, object layer, message filtering, message and status handling, transfer layer. Most of the CAN standard applies to the transfer layer. The transfer layer receives messages from the physical layer and transmits those messages to the object layer. The transfer layer is responsible for bit timing and synchronization, message framing, arbitration, acknowledgement, error detection and signaling, and fault confinement. It performs fault confinement, error detection, message validation, acknowledgement, arbitration, message framing, transfer rate and timing, information routing, physical layer. CAN bus originally specified the link layer protocol with only abstract requirements for the physical layer, for example, asserting the use of a medium with multiple access at the bit level through the use of dominant and recessive states. The electrical aspects of the physical layer were specified in ISO 11898-2 2003, which is now widely accepted. However, the mechanical aspects of the physical layer have yet to be formally specified. As a result, an automotive ECU will typically have a particular often custom connector with various sorts of cables, of which two are the CAN bus lines. Nonetheless, several de facto standards for mechanical implementation have emerged, the most common being the 9-pin D subtype male connector with the following pin out, pin 2, CAN low, pin 3, G and D, pin 7, CAN high, pin 9, CAN V+. This de facto mechanical standard for CAN could be implemented with node having both male and female 9-pin D sub-connectors electrically wired to each other in parallel within the node. Bus power is fed to a node's male connector and the bus draws power from the node's female connector. This follows the electrical engineering convention that power sources are terminated at female connectors. Adoption of this standard avoids the need to fabricate custom splitters to connect two sets of bus wires to a single D connector at each node. Such non-standard wire harnesses that join conductors outside the node reduce bus reliability, eliminate cable interchangeability, reduce compatibility of wiring harnesses, and increase cost. The absence of a complete physical layer specification freed the CAN bus specification from the constraints and complexity of physical implementation. However, it left CAN bus implementations open to interoperability issues due to mechanical incompatibility. Noise immunity on ISO 11898-2 2003 is achieved by maintaining the differential impedance of the bus at a low level with low-value resistors at each end of the bus. However, when dormant, a low-impedance bus such as CAN draws more current than other voltage-based signaling buses. On CAN bus systems, balanced line operation, where current in one signal line is exactly balanced by current in the opposite direction in the other signal, provides an independent, stable 0V reference for the receivers. Best practice determines that CAN bus balanced pair signals be carried in twisted pair wires in a shielded cable to minimize RF emission and reduce interference susceptibility in the already noisy RF environment of an automobile. ISO 11898-2 provides some immunity to common mode voltage between transmitter and receiver by having a 0V rail running along the bus to maintain a high degree of voltage association between the nodes. Also, in the de facto mechanical configuration mentioned above, a supply rail is included to distribute power to each of the transceiver nodes. The design provides a common supply for all the transceivers. The actual voltage to be applied by the bus and which nodes apply to it are application-specific and not formally specified. Common practice node design provides each node with transceivers which are optically isolated from their node host and derive a 5V linearly regulated supply voltage for the transceivers from the universal supply rail provided by the bus. This usually allows operating margin on the supply rail sufficient to allow interoperability across many node types. Typical values of supply voltage on such networks are 7 to 30 V. However, the lack of a formal standard means that system designers are responsible for supply rail compatibility. ISO 11898-2 describes the electrical implementation formed from a multi-dropped single-ended balance line configuration with resistor termination at each end of the bus. In this configuration, a dominant state is asserted by one or more transmitters switching the CAN to supply 0V and switching CAN plus to the plus 5V bus voltage, thereby forming a current path through the resistors that terminate the bus. As such, the terminating resistors form an essential component of the signaling system and are included not just to limit wave reflection at high frequency. During a recessive state, the signal lines and resistor, S, remain in a high impedances state with respect to both rails. Voltages on both CAN plus and CAN tend towards a 1/2 rail voltage. A recessive state is only present on the bus when none of the transmitters on the bus is asserting a dominant state. During a dominant state, the signal lines and resistor, S, move to a low impedance state with respect to the rails so that current flows through the resistor. CAN plus voltage tends to plus 5V and CAN tends to 0V. Irrespective of signal state, the signal lines are always in low impedance state with respect to one another by virtue of the terminating resistors at the end of the bus. This signaling strategy differs significantly from other balanced line transmission technologies such as RS-422/3, RS-485, etc., which employ differential line drivers/receivers and use a signaling system based on the differential mode voltage of the balanced line crossing a notional zero of E. Multiple access on such systems normally relies on the media supporting three states and is dealt with in the time domain. Multiple access on CAN bus is achieved by the electrical logic of the system supporting just two states that are conceptually analogous to a Euro-wired or a Euro-unregistered trademark network. Frames. A CAN network can be configured to work with two different message formats, the standard or base frame format, and the extended frame format. The only difference between the two formats is that the CAN base frame supports a length of 11 bits for the identifier, and the CAN extended frame supports a length of 29 bits for the identifier, made up of the 11-bit identifier and an 18-bit extension. The distinction between CAN base frame format and CAN extended frame format is made by using the IDE bit, which is transmitted as dominant in case of an 11-bit frame, and transmitted as recessive in case of a 29-bit frame. CAN controllers that support extended frame format messages are also able to send and receive messages in CAN base frame format. All frames begin with a start of frame bit that denotes the start of the frame transmission. CAN has four frame types: data frame, a frame containing no data for transmission; remote frame, a frame requesting the transmission of a specific identifier; error frame, a frame transmitted by any node detecting an error; overload frame, a frame to inject a delay between data and or remote frame; data frame, the data frame is the only frame for actual data transmission. There are two message formats: base frame format, with 11 identifier bits; extended frame format, with 29 identifier bits. The CAN standard requires the implementation must accept the base frame format and may accept the extended frame format, but must tolerate the extended frame format. Base frame format. The frame format is as follows. Extended frame format. The frame format is as follows. The two identifier fields combine to form a 29-bit identifier. Remote frame. Generally, data transmission is performed on an autonomous basis with the data source node sending out a data frame. It is also possible, however, for a destination node to request the data from the source by sending a remote frame. There are two differences between a data frame and a remote frame. Firstly, the RTR bit is transmitted as a dominant bit in the data frame, and secondly, in the remote frame there is no data field. That is, RTR equals 0A. Dominant in data frame, RTR equals 1A. Recessive and remote frame. In the very unlikely event of a data frame and a remote frame with the same identifier being transmitted at the same time, the data frame wins arbitration due to the dominant RTR bit following the identifier. In this way, the node that transmitted the remote frame receives the desired data immediately. Error frame. The error frame consists of two different fields. The first field is given by the superposition of error flags contributed from different stations. The following second field is the error delimiter. There are two types of error flags: active error flag, 6 dominant bits are transmitted by a node detecting an error on the network that is in error state error active. Passive error flag, 6 recessive bits are transmitted by a node detecting an active error frame on the network that is in error state error passive. Overload frame. The overload frame contains the 2-bit fields overload flag and overload delimiter. There are two kinds of overload conditions that can lead to the transmission of an overload flag: the internal conditions of a receiver, which requires a delay of the next data frame or remote frame. Detection of a dominant bit during intermission. The start of an overload frame due to case 1 is only allowed to be started at the first bit time of an expected intermission, whereas overload frames due to case 2 start 1 bit after detecting the dominant bit. Overload flag consists of 6 dominant bits. The overall form corresponds to that of the active error flag. The overload flag unregistered trademark S form destroys the fixed form of the intermission field. As a consequence, All other stations also detect an overload condition and on their part start transmission of an overload flag. Overload delimiter consists of 8 recessive bits. The overload delimiter is of the same form as the error delimiter. Interframe spacing, data frames and remote frames are separated from preceding frames by a bit field called interframe space. Overload frames and error frames are not preceded by an interframe space and multiple overload frames are not separated by an interframe space. Interframe space contains the bit fields intermission and bus idle, and suspend transmission for error passive stations, which have been transmitter of the previous message. Interframe space consists of at least 3 consecutive recessive bits. Bit stuffing: in CAN frames, a bit of opposite polarity is inserted after 5 consecutive bits of the same polarity. This practice is called bit stuffing, and is due to the non-return to zero coding adopted. The stuffed data frames are destuffed by the receiver. Since bit stuffing is used, 6 consecutive bits of the same type are considered an error. Bit stuffing implies that sent data frames could be larger than one would expect by simply enumerating the bits shown in the tables above. Standards: the CAN data link layer protocol is standardized in ISO 11898-1. This standard describes mainly the data link layer sublayer and the media access control sublayer, and some aspects of the physical layer of the OSI reference model. All the other protocol layers are the network designer's choice. There are several CAN physical layer and other standards: ISO 11898-1, CAN data link layer and physical signaling, ISO 11898-2, CAN high-speed medium access unit. ISO 11898-2 uses a 2-wire balanced signaling scheme. It is the most used physical layer in car powertrain applications and industrial control networks. ISO 11898-3, CAN low-speed, fault-tolerant, medium-dependent interface, ISO 11898-4, CAN time-triggered communication. ISO 11898-4 standard defines the time-triggered communication on CAN. It is based on the CAN data link layer protocol providing a system clock for the scheduling of messages. ISO 11898-5, CAN high-speed medium access unit with low power mode, ISO 11898-6, CAN high-speed medium access unit with selective wake-up functionality, ISO 11992-1, CAN fault-tolerant for truck-trailer communication, ISO 11783-2, 250 kbits, agricultural standard. ISO 11783-2 uses 4 unshielded twisted wires. 2 for CAN and 2 for terminating bias circuit power and ground. This bus is used on agricultural tractors. This bus is intended to provide interconnectivity with any implementation adhering to the standard. ISO 15765-2, also called ISO TP, is a standard for flow control and handling of messages larger than 8 bytes. SAJ 1939-11, 250 kbits, shielded twisted pair, SAJ 1939-15, 250 kbits, unshielded twisted pair. The SAJ 1939 standard uses a 2-wire twisted pair, A11 has a shield around the pair while A15 does not. SA 1939 defines also application data and is widely used in heavy-duty and autobus industry as well as in agricultural and construction equipment. SAJ 2411, single-wire CAN, higher layer implementations, as the CAN standard does not include tasks of application layer protocols, such as flow control, device addressing, and transportation of data blocks larger than one message, and above all, application data. Many implementations of higher layer protocols were created. Several are standardized for a business area, although all can be extended by each manufacturer. For passenger cars, each manufacturer has its own standard. Among these implementations are, ARINC 825, CAN Aerospace, CAN Kingdom, CANopen, CCP/XCP, DeviceNet, Energy Bus, GMLAN, ISO 15765-4, ISO 11783 or ISOBUS, ISO 14229, SAJ 1939, ISO 11992 for heavy trailers, MILCAN, NMEA 2000, RVC, Safety Bus P, Smart Craft, Smart Distributed System, VSCP, Security. CAN is a low-level protocol, and does not support any security features intrinsically. Applications are expected to deploy their own security mechanisms. For example, to authenticate each other. Failure to do so may result in various sorts of attacks, if the opponent manages to insert messages on the bus. Password mechanisms exist for data transfer that can modify the control unit software, like software download or ignition key codes, but usually not for standard communication. Development tools. When developing and/or troubleshooting the CAN bus, examination of hardware signals can be very important. Logic analyzers and bus analyzers are tools which collect, analyze, decode and store signals so people can view the high-speed waveforms at their leisure. There are also specialist tools as well as CAN bus monitors. Licensing. Bosch holds patents on the technology, and manufacturers of CAN-compatible microprocessors pay license fees to Bosch, which are normally passed on to the customer in the price of the chip. Manufacturers of products with custom ASICs or FPGAs containing CAN-compatible modules may need to pay a fee for the CAN protocol license. See also, Betaflight, car audio, CAN bus monitor, list of software applications to monitor the activity on the CAN bus, CAN for Linux a open source Linux device driver for CAN, FlexCAN a an alternative implementation. FlexRay a possible future direction, list of network buses, local interconnect network a low-cost alternative. OBDEP IDs, list of parameter IDs, OSEK, socket CAN a set of open source CAN drivers and a networking stack contributed by Volkswagen Research to the Linux kernel. References. External links, Wiki on CAN technology and products, Bosch specification, Bosch CAN FD specification version 1.0, controller area network schedulability analysis, refuted, revisited and revised, pinouts for common CAN bus connectors, independent discussion platform CAN list, free tutorials and low-cost development tools, a web page about CAN in automotive, controller area network schedulability analysis with FIFOQs, controller area network implementation guide, free tutorial, controller area network introduction and fundamentals, freeware bit timing calculator for Windows, supports a lot of microcontrollers, for example Atmel, STM32, microchip, Renesas. CAN protocol tutorial.